Hi. Today I could do with a snack. How about you? As usual, just take a watch, take a listen, and write down any questions you have.
This demonstration, I'm using a vacuum chamber. This vacuum chamber, I have placed two marshmallows inside. Now, marshmallows are colloids. They're air puffed into some kind of sugary polymer that we love to eat. And this hose is connected to a vacuum pump that draws the air out and
Oh.
lowers the pressure.
Let's stop him from talking and jump to the fun part.
Something interesting happened. They expanded or increased the pressure by air coming back in. Oh, that was a flip. I like that one. These guys decreased in volume because
All right. And then finally, I think he brings up one to show what the original was for a basis of comparison. So there you
it
go.
looks like to me
That should be enough to get some questions. I just didn't want to bore you. I can give you a link to this full video if you want. I believe this is Mr. Grodsky chemistry. For the next few videos, for the next few lessons, we're going to be doing a similar procedure. He mentioned the word variable a couple times in the video. There were some other words that he mentioned. He said amount of gas, maybe some temperature, and the word volume might have jumped in there. When it comes to gases, particularly gases that undergo physical changes, there really are only four different quantities that we're concerned about, and they're listed there. And in each of the cases, and in every scenario, these are all controlled demonstrations to hold some of those conditions, those quantities constant, or to vary them. So like he said, that's a vacuum chamber hooked up to a pump. The pump works by pulling out air. There's a little scoop inside this box that would grab air. There's like a sealed container where it grabs air and it pulls it aside, and so your hose is going off to your container, and then inside the container you'll build up a vacuum, and a vacuum is a space devoid of matter. That should ring some bells if you're not super familiar with it. That relates most directly of these four quantities to pressure. And then also we had a visible evidence of a change in size, and of those four, that would be volume. So of these four quantities, we're going to say that volume and the pressure are the variables, and temperature, I didn't see any refrigeration or heating apparatus, so that's going to be a constant. And then we're also going to say, within reason, there's a little asterisk there that I'm going to have to put there. The amount of gas is a constant. Yes, the marshmallows did end up smaller after the fact than they started, but there's a very important reason for that, and we'll talk about that on the next slide. Something else I did want to mention before we got too much further with all of these, since these are controlled experiments, they have independent variables and dependent variables. So what is changed and what changes in response. In this case, the vacuum pump, since it's a pump and it's a vacuum, we're going to say that pressure is our independent variable and the size, or the volume, is our dependent variable. Now, in terms of how the vacuum pump works, I did include these two GIFs. I wanted to put a little bit something else for you to see. And if you have one of these at home, you can do it. This is a fun game to play. These are just syringes. I think you can use them for like flavor injectors for cooking. The top one says unsealed, so there's an opening at the bottom. So when you pull the plunger, air just rushes in as you pull to take the space that you're opening up. But if you cover the end with your thumb, it becomes a sealed container. So that when you pull, no new matter comes in, and the matter that's there has a different spread. It spreads out because gases have variable, indefinite volumes. But like I said, marshmallows, a little bit harder to talk about, so I want to shift a little bit to balloons. If you want, you could think of a marshmallow as, like he said, a sugary polymer with several little bubbles of air in them. Now the problem is, as the marshmallow expands, the whole marshmallow expands, and those little air pockets start to rupture. And if they rupture, then the air can get out, and so then it would end up all shrivelly and like gross, which, well, actually, it still tastes the same. It's just not as fluffy, so gross might be a relative term. this is why I want to talk about balloons. As you can see in the image here, the balloons contain a certain amount of gas. There's gas outside the balloon. The particles can bounce against the sides of the balloon, and the sides of the balloon don't break. Again, asterisk, within reason. It is interesting to note that in these vacuum chambers, I don't think the balloons ever fully rupture. I mean, don't quote me on that, but I've never had one, knock on wood, rupture on me. So how do the particle arrangements outside the balloon and inside the balloon change? I think we should draw a few different images here. First, there's our balloon, our marshmallow, before we have the vacuum pump on, hose going off to the side. Then, let's have our balloon at some later time, the vacuum pump has been running. If we're talking about this on the particle level, like you see in this image here, this image would correspond directly to the image down here. It's just this is a macroscopic view. You can say that inside the container is a gas. All those gas particles are spread out, and they're fully spread out and evenly distributed around the container. Of course, they're all moving because, they have temperature associated with them. As the vacuum pump works, there's fewer and fewer particles. It literally sucks the matter out of the container. That's the vacuum part of the vacuum chamber. So what that does is the particle arrangement becomes far less dense outside the balloon. Inside the vacuum chamber, but we're not worried about, there's gas out here. That's a solid container, so they're just going to bounce off the sides, and we're not going to worry about those. The amount of matter inside the balloon is constant. So let's try and pick this apart a little bit. If pressure is force over area, force comes from the collisions. The more collisions, the more force, or the harder the collisions, I guess, the more force. So there's a certain amount of force on the outside of the balloon and a certain amount of force on the inside of the balloon. If the balloon is not changing in size, the pressure inside the balloon is equal to the pressure outside the balloon. That should make sense. If the push out and the push in are equal, it stays the same. So the only time that you're going to get a change in size of the balloon is if they're not equal. Now, when we say P1 and P2 here, I'll reference this later, we're going to say time 1 and time 2. That's what these subscripts 1 and 2 mean. So let's call this P1 and this P2, right? Smaller balloon, larger balloon. So to take a look at it, it looks like since there are fewer gas particles and we're still at the same temperature, there's a lower force on the outside of the balloon. So P1 would be greater than P2. And then right before we get to this time 2, as the balloon is expanding, that must be because the pressure inside is greater than the pressure outside. The balloon is losing air on the outside, so there's fewer collisions. Imagine these outer particles not colliding. There's all those collisions on the inside, and so there will be an imbalance, a push out. Now here's the thing about pressure. That area is still there too. If the balloon gets bigger, then the area goes up. Force over area goes down, right? 1 over 2 versus 1 over 3 versus 1 over 4. So what will happen is that as the balloon expands, the pressure inside will also decrease. And if you turn off the vacuum pump and stop sucking out air and there's some air left, then at some point the balloon expanding, there's less pressure on the outside, but now because the balloon is bigger, there's less pressure on the inside. So then eventually the expansion will stop when the pressure inside is again equal to the pressure outside. Don't get me wrong, these two pressures on the bottom are probably lower, but equal. And so that you can play this game if you have the ability to control pressure, where the pressure will dictate how the things inside these containers that the pressure is changing behave. And that leads us to a little bit more talking about like math and formulas and chemical and physical laws. So for everything you've heard so far, we should come up with a relationship that describes this. As I like writing as variable, and then we talk about other variable, right? So we've got our independent variable and our dependent variable. I don't know if you're familiar with writing hypotheses or coming up with these relationships, but this is a simple way to write it. As pressure does this, volume does this. From what we've seen, there was a decrease in pressure because of the vacuum. That's what vacuum means, lower pressure. And I've seen that the volume goes up. The balloon got bigger. And then as the pump was, as you took off the hose, right, the air rushed back in. The pressure then increased. As pressure increases, volume, then the marshmallows shrank. So because one's going up and the other's going down, we're going to call this an inverse relationship. That's our definition of inverse. One goes up, the other goes down. So what would that graph look like? Well, it might kind of make sense where, if pressure's increasing, right, going up, that's on the x-axis, going to the right, and volume's getting smaller. So at certain time, we've got, a low pressure and a high volume, and some other time we've got a high pressure and a low volume, right? That should correspond to what we saw. Well, then maybe I would just expect that, right? There's your line. This nice downward slope, inverse relationship. One goes up, the other goes down. Except if we were to actually label these and put numbers, this is the origin, this is the positive direction, and there is a negative direction down here. And this yields a very interesting question. Is there such a thing as negative pressure? Right? You can decrease the pressure, but if pressure comes from force, I'm not 100% sure you can have negative force with respect to, gas particles. I know in physics you can have negative force because there's a positive and negative direction, but in terms of the force exerted due to air, you can't have negative air. And to that point, you can't have negative volume, right? Volume is a measure of the amount of matter present. So I don't know what negative matter is. That's not even a thing. So no, you can't really have this happen, these two areas. So this is not going to be what we go with. We can't use this. We do still want to show this relationship, whereas one increases, the other decreases. But I don't think we can cross over these lines, the line for volume and the line for pressure. Those represent zero pressure and zero volume, respectively. So what we want to do is we want to show that they are going to get close but never touch. If we wanted to put this relationship into words without too many numbers, here are some examples that I pulled from a textbook. Take a look at these numbers. As pressure doubles, volume gets cut in half. And that seems to happen again. Or another way, to look at all the way over, it seems like when the pressure is quadrupled, the volume is cut back by a quarter. So if the pressure went up by 100, the volume would go down to 1/100th. But that means like the higher the pressure goes, you'll never quite get to zero, right? If the pressure goes up by 1,000,000, you're dividing by 1,000,000, and 1/1,000,000 is still not zero. It's just a small number. And what you'll see is you could still even have those same dots present, but what you would see is this graph would start to approach this zero pressure, and this graph would start to approach this zero volume and never quite reach it. In math, that's called an asymptote. And so this is the graph. This is what we're going to go with. I stretched it beyond the limits of the picture, but that's easily remedied. There's our relationship between pressure and volume. You're always sliding along that line. At any given point, you can find the pressure and the volume corresponding to this sample of gas. Now, of course, don't forget, this all completely relies on a sample of gas where the temperature and the amount of gas present are constant. This is why it needs to be a sealed container, or this is why we're looking at balloons. As soon as that amount of gas is not constant, all of the math of this relationship falls right out the window. Speaking of math, if you take those numbers, we can describe this relationship mathematically. Most of the relationships we're going to see in this unit are based off of simple multiplication and division. So we did see that whole if you double one, the other doubles. But what I more want to think about is what is the relationship between the pressure and the volume at a given time. If you want to think about it this way, we can call this P1 and V1, and this is P2 and V2, and this is P3 and V3, right? These subscripts just refer to different times. So at time 1, there's a certain pressure and volume. We increase the pressure, the volume is seen to decrease, right? There's our independent-dependent variable. I think if we want to come up with some sort of mathematical relationship that ties them all together, we should multiply them. And I have a good reason for that. If you multiply the pressure and the volume for this sample of matter, you always get the same thing. You're not going to get the same, you're not going to get the same number every time. I'm not saying that every time you multiply the pressure and the volume for any sample of gas at any temperature, you always get 1. But for that sample, as long as the temperature and the amount of gas don't change, the product of pressure and volume will always be a constant. In math and in chemistry, we refer to constants with the letter K. I think there are too many C's when it comes to chemistry between specific heat and carbon and Celsius. So we use a lowercase k to say constant. In other words, in math, pressure times volume at any given time is equal to a constant. And this graph, if you're familiar with, xy equals a constant, is known as a hyperbola. Not a hyperbole, that's something different. If you've ever seen those graphs before, you probably recognize this image here. Hyperbolas go back down into the third quadrant too, where they're both negative. We don't do that because, again, no negative pressure, no negative volume. This relationship has a name. We still have more of these scientists that did plenty of work that we stand upon today to see past their shoulders. This one is named after Boyle. I believe he was an English chemist or physicist. He did the work. The law got named after him. And just to be clear, I think I've talked about this before, but it's worth mentioning again. Don't forget that laws describe what happens, and theories try and describe why they happen. So we're not trying to say why are pressure and volume inversely proportional. I'm just trying to say that they're inversely proportional. We'll deal with why some other time. And as we saw before, that can be written as PV equals K, or if PV at time 1 equals K and PV at time 2 also equals K, you could also just say that P1 times V1 equals P2 times V2. Yeah, and you can keep doing that, but usually we only worry about 2 different time frames. So to solidify this up for you, I want you to take a look at these 2 problems. Just like we did with the heat calculations, I think it's valuable to go through and underline words and write and circle and say what are these things so that you can then figure out what formulas you need and how you're filling in. So let me do that first. So based on what I have here, you've got a balloon. It says 5 liters and 3 atmospheres, right? Liters, atmospheres, those are units of volume and pressure respectively. That's our initial, our 1. And then it says final volume at the end, so that's V2. Since this is all based on Boyle's law, let's rewrite our formula and then start to substitute in. Of course, we don't know V2, so we're going to leave that as our variable. If you want to call it X, you can. And then we do some simple algebra. The numbers and the units cancel. You'll cancel your atmospheres there so that you end up with just liters. And what you come out with is 2.4 liters when you do this. There is a conceptual checkpoint here. Does the answer make sense? Well, what happened to the pressures? Pressure went from 3 to 6.2. Pressure went up. As pressure goes up, volume goes down. Is my answer less than 5? Well, yes, it is. So that's good. That's a sign that we got the right answer. That's a way you can be sure of your work. If you want to do this second one on yourself, go ahead and hit that pause button. Otherwise, I'm just going to start doing the work again. Let me change colors. We're looking for what is the volume, so we want our V2 again. So it's the same exact setup. I'm just going to copy that down. And then let's plug in our numbers. 2 things worth mentioning. 1, it doesn't matter what the units are for pressure or for volume, as long as they're the same. It doesn't matter whether you're working in atmospheres or kilopascals. You just need to use the same units on both sides of the equation. If you don't have the same units on both sides, if you have like kilopascals and atmospheres in the same problem, you need to convert. But you probably won't have that happen. And then I was surprised to find out. I went and looked this up. That's a really low pressure for an airline, but I guess that's what they do. It's higher than it would be if the windows were open, but that still seems 75% of what normal pressure is. That's a lot. But what we come out here is 20.2 liters. Now again, does this make sense? Well, pressure went down, so volume should go up. 20 is greater than 15, so this works. Thanks for watching.